Alrighty. I will.
Every American feels like they're
I will begin with a word of prayer. All right, I will begin. Dear Father, we thank you for this day. Again, I thank you for this class and just ask you to bless our work today. Help us to glorify you we do, and help us to find any errors early when they happen. In your name I pray, Lord Jesus. Amen. All right, I guess I owe you the clarification of the cliffhanger. I will start out. Well, this isn't really the cliffhanger, but let me just start out with this little picture, which is the thing I got twisted. So I looked this up in a genuine physics book. It has to be right. So the velocity is the angular velocity across R, and the picture for that would be something like, we've got let's see here, like a circle, and omega is like this, all right? This has radius r, let's say. I put the origin down here. So put the radial vector up like this. All right. And then let's see here. So we do omega. Omega. Man, I have a hard time doing this. Omega crossed into R, straight into the board, which I could either draw as like a circle. I guess I could draw it like this, if you like. The other way to draw it might be, well, let me not. Let's see here. If I was to go to this point right here, right? This other R, right? We call this R1. Let's call this R2. Here's V1. And then I do omega crossed into R. Then my V would be like this, all right? Which makes sense, right? It's perpendicular to both the radial vector from the origin as well as the angular velocity. So the angular velocity, and this is for circular motion, of course, the angular velocity points in the direction of the radius, the direction of the axis of rotation. And in this context, we can write the following equation, right? Like V is equal to, R omega, which is R times d theta dt in this context, right? Where theta is going to be, like the angle swept out in this circle, right? Like if I was to foolishly attempt to draw it, if I could maybe make this theta, right? If I made this theta equals to 0, let's say, as it sweeps around, you're going 0 to 2 pi, and round and round and round she goes. That's the deal. So I got it flipped around last class somehow. Sorry about that. And then the other comment, of course, is if motion is nice, right, then the angular momentum is simply equal to the moment of inertia times omega, right? So here I'm assuming, of course, that, and by nice here, I just mean that we're talking about, circular motion about axis with which the moment of inertia I is, is given. If the motion is more complicated, then, so here, I mean for this just to be a scalar, all right? I indicated last class to you guys that that's part of a broader story where you replace the scalar with a matrix, and then you need the inertia, so-called inertia tensor, to take care of that that broader case. All right, great. So let us get back to the cliffhanger. Let us expose the the source of the transgression. So example 1, we had let's see here, we had a pulley, right? And the radius of the pulley was r, and it had mass m, right? And we put a string, right, off the pulley, and the string was supposed to, grip to the pulley without slipping. And down at the bottom of that string, we put another mass, little m, right? And then somehow or another, I managed to, so we said that this was a disk, right? So the moment of inertia, 1/2 big M r squared as we derived, right? And then after a little bit of, mathematics and seemingly reasonable equations, we found ourselves face to face with the acceleration being twice gravity, which seems wrong, right? I mean, it's wrong, right? This isn't exactly the same thing, but it's kind of the same thing in reverse, right? I'm just letting the pulley drop, That doesn't, it's not faster than free fall, right? If I was to drop something, it would drop faster than that, right? Here, watch. Right? Oh no, it's coming apart. Oh well, don't tell Dr. Dinsmore. So obviously it shouldn't fall twice g. So what was the error in what I did last time? Yeah? I told one of you, so one of you can't answer. But let's go through it. So here we go. Let us suppose that this rotates with angular acceleration alpha. So one of the things I said that the acceleration is equal to r alpha. That was not the mistake. That's totally legitimate. If the string does not stretch and it without slipping is attached to the pulley, the massive pulley, then that is true. That's true. I also said that I times alpha was equal to the net torque, right? And I said that the net torque was the tension force, right, that the string puts on the pulley right here, right, like this basically. And so I was like, well, the tension, because it's applied tangentially to the circle at a distance r from the pivot point, the tension is simply RT, right? Not the tension, the torque is RT, right? And you might say, well, maybe that's the mistake. No, that's not the mistake. That's also totally fine, all right? So the other thing we did was I just said, oh, the tension's equal to mg. That was nonsense. But you guys believed me, right? Because you had a bad teacher earlier this semester, so maybe you failed this class. I can blame your previous instructor, right? No? No recycling? Okay. So the thing is, we have to think about the free body diagram down here. We've got the tension going up. We've got mg going down. And yes, they would be equal if this was in equilibrium. Is this in equilibrium? No, it's accelerating. We must face Newton's second law. M times A is equal to, let's see here. I'm taking this as positive, so that makes mg positive, right? Mg minus the tension. So since the acceleration is non-zero, the tension is not equal to mg. That was the source of our error, all right? But it was a very believable error, so I'm proud of it, you know? It was a nice clean error. All right, so there's different ways to go about here. So notice that one thing we could do would just be to, like, let's take the equation above and clean it up a little bit. This is 1/2 m r squared alpha equals to RT, right? Which gives us 1/2 m r alpha equals to T. But R alpha is what? R alpha is A, right? So I have big M over 2 times A is equal to T. That's what this becomes, all right? So I have Newton's second law in the linear sense from the little mass, and I have Newton's second law in the rotational sense from the pulley, right? The I alpha equals to torque, that's the rotational Newton's second law. Now I've got two equations, two unknowns. We know what to do. The answer is algebra. So I will take these and I will add. And that will give me little m plus big M over 2 times the acceleration we don't know is equal to mg. Because the tension, they'd be canceling. Right? So what does this tell me? This tells me that the acceleration of this system is equal to mg divided by little m plus big M over 2. Yeah, that's the acceleration. And I think that was my question I raised last class, is what's the acceleration of this system, right? And we got twice g. I feel better, right? We got twice g in what context? What did we pick? We picked when the masses are equal. That was the special case we looked at. So let's look at that again. If little m is equal to big M, then the acceleration is actually equal to what? mg over m plus little m over 2, also known as g over, looks like 3/2. So the answer is 2g over 3. I like this much better. Yes, the acceleration should be less than gravity, not more. I feel much better. Do you guys feel better? Yeah. Can you tell me how does energy work for this system? Where is the energy? If we start out with it motionless, we have two kinds of energy, right? Well, I mean, tension, I'm not sure there's any energy in tension directly, but we have potential energy of m, right? And as the thing accelerates, we're going to get kinetic energy, both of the little m and also the pulley, right? So we could study energy would be conserved in this system because there's no friction there's no friction taking away kinetic energy here. So we could study conservation energy for this problem if we wanted to. Any questions? So long story short, we must be careful to not assume equilibrium equations when we're not in equilibrium, all right? Let's look at another example. Let us suppose that we have a table, all right, and then we have a pulley here, and we've got a mass, and that mass is connected around the pulley to another mass. Let's call this mass M2. We'll call this mass up here M1. All right? And we'll say that this pulley has mass big M again, right? So this time the moment of inertia will be boring. We'll say it's a disk again. So the moment of inertia of the pulley is 1/2 I omega squared, 1/2 mr squared. Perhaps we should put friction back into the mix here. Let us assume that there actually is friction on this tabletop between M1 and the surface, right? Let's actually consider that. And let's try to write down the equations of motion in this situation, all right? So we're going to suppose that, friction coefficient mu for M1. And just to keep things relatively simple, I guess we will suppose it's moving. All right. So let's suppose that we have an initial velocity v naught that's given, and it's non-zero, which puts us decidedly in the kinetic regime, right? So how do we solve this problem? What are we up against here? So let's go through it bit by bit. First of all, we'll do the easy part. M2 is kind of the easy part. We've got M2G going down, and what do we have going up? We have, let's call it the tension on mass 2. Let's call it T2. All right? We got T2 there. So this gives me Newton's second law, M2A is equal to, I'm going to take the motion to be this way, to be positive, all right? So M2G minus T2. I think that's it, right, for M2. That's the one thing. Now let's look at it. We also have M1, right? So M1, I'll draw the free body diagram here. We've got, on the one hand, we've got the tension on mass 1, like that, right? And we also have the normal force, like that. And we've got, of course, M1G going down, and the friction force, I guess, it's better go this way, right? Anything else here on M1? I mean, we could add a little dude pushing on it at an angle if you want, but let's not do that. Right? I'll say that for the final. I'm sorry, too soon. So that, lo and behold, well, there's a couple things that I learned from this. One of the things I learned from this is that the normal force is what? Is M1G, because we're on a horizontal plane, and so the normal force is the weight, thankfully, which means the force of friction we can straight calculate as mu times M1G. Well, that's nice. So then we have M1A is equal to what? Well, this time the tension goes in the positive sense. So I put T1, all right, minus the force of friction, which in this case is mu M1G. All right, so we did Newton's second law on the first mass, the second mass. What's left? The pulley. So one of the things I just did now, without thinking about it, it's not really true. I thought about it before. There was a time in my life when I just said, those are the same tensions. And then I got really confused because it didn't make sense. All right? That's the fundamental error that students might make here, is assuming we have the same tension on both halves of the string. But when this pulley is massive, it doesn't have to be the same tension on both sides. All right? That's how it works. So because of that, we don't have to have T1 is equal to T2. Before we assumed that, it had to be the case when the pulley was massless. There was nothing for the tension to pull on in the middle in the sense of that the pulley is here. So, but here we have the Newton's second law for the pulley, which is 1/2 big M r squared times the angular acceleration. And notice how this works. Don't be deceived. T2 doesn't point up here. That would be physically absurd, wouldn't it? Does T2 push the pulley up? No. T2 does what? You're like, wait a minute. You just said T2 is pointing up. Now you're saying it's pointing down. Which is it, up or down? It's both. The rope pulls up on the mast down there, and it pulls down on the pulley. Tension is the value with which it pulls on both ends. And it pulls on different directions on the opposite ends of the rope. This is how ropes work. All right, but we call both of them T2 because in terms of magnitude, they have the same magnitude, but of course they have different direction. Physically speaking, they have to. Right? Otherwise I'd be saying the rope is pushing the pulley upward, which is just crazy, right? Or equally crazy that the rope is pushing the mast downward, right? Anyway, slice it. Now over here, T1 goes like this, all right? Now they're both applied tangentially, so the torque in both of these cases is simply the radius times the force applied, all right? So you guys tell me, if this is the positive direction, which one produces a positive torque? Which one produces a negative torque? T2 is a positive torque, so I do T2R minus T1R. And that's it. These are the equations of motion which govern the system. And of course, also you have, if the rope doesn't slip, which we're assuming, we also have the fundamental relation that the acceleration of the system is the radius of the pulley times the angular acceleration of the pulley, right? So we can take this last equation and we can rewrite it as 1/2 m times the acceleration is T2 minus T1. All right? Why would you want to do that? Yeah, so we can add it to the previous equations, right? Because adding equations is way easier than substituting. Is it not? Which do you like more, adding equations or substituting? I like adding equations when I can get away with it. It tends to be much faster than substituting, especially with something like this, where you see that these equations are like staggered. So if I add all three of them together, what happens? I get, M2 plus M1 plus 1/2 big M all times A. You said the T's disappear. I think you're right. We get, M2G minus mu M1G, right? And the T1 cancels with the T1s, they be canceling, the T2s, they be canceling. So yeah, that's it. So the acceleration of the system is M2 minus mu M1 all times G divided by M1 plus M2 plus 1/2 big M. All right? And then, of course, we could answer other questions like a variety of other questions, kinematically, if we wanted to. So is it just going to keep sliding? Like, what's going to happen with this system? Oh, yeah, stop when M2 hits the ground. That was not what I was looking for, but yes, thank you. That is a very common sense, good answer to my question. Imagine that the ground is infinitely far away. Let's let this table, this is a 100-meter tall table. Mass one hits the pulley. Oh, also a totally reasonable answer, but not the one I'm thinking about. Let the mass one be like a kilometer away from the pulley. Now that we've made this problem thoroughly unphysical, let's do a physical analysis. what I'm trying to get at is does the acceleration ever drop to like 0? I mean, I guess the acceleration is constant, isn't it? Yeah, hold on a second. So either, I guess either the acceleration is positive, right, or it's negative. If the acceleration is positive, what's happening? It just keeps falling faster and faster, right? If the acceleration is negative, it's going to slow down, right? And then I guess at some point, if it slows to 0, maybe you're stuck in, well, I don't know, does that make you static? That's a good question. Like, how long do you have to be stopped before it becomes static friction? I don't have a good answer to that. Let's see here. What's the energy for the system? Let's try to write that down. So if I want total energy is equal to 1/2 m1, let's say, I'm going to write the initial energy here, m1 v naught squared plus 1/2 I omega 1 squared, right? Plus 1/2 m2 v naught squared, right? And then let us define the height of this thing to be h2, right? So plus m2g h2, right? This would be the initial energy, right? What would the final energy be equal to? Can you simplify this piece right here? What is this actually? Let's talk about that for a second. This is 1/2 of 1/2 mr squared, right? Times v naught over r squared. So that's actually 1/4 m v naught squared. The rotational energy here of the system initially would be 1/4 big M v naught squared. Right? So there's kinetic energy in the spinning of the pulley, in the translational motion of mass 1 and the translational motion of mass 2, right? Respectively, horizontally and vertically. And so great. The final energy is going to be 1/2 m vf squared, 1/2 m1. Let me just get to the point here. We can factor out 1/2. We got an m1 plus m over 2, right? Plus m2, all of that times vf squared, right? That, I'm just combining all of the kinetic energy terms together into one foul swooping thing, right? Glom them all together there. They're just all that. And then you have plus m2g, the final position here, right? I'm assuming that we're not transitioning off the tabletop, right? So like the potential energy of m1 stays the same, all right? And I have looped in this big M over 2 accounts for the rotational kinetic energy, right? But is E not equal to EF in this situation? Certainly not, right? We have to do what? Subtract what? Minus the energy lost to friction, which would be what? It would be, I believe, H2 minus, not H2, what did I call it before? I did call it H2. I should have called that H sub naught. I'm going back. That's H sub naught. It's not too late. So, oh, I'm sorry, that was horrible. So H naught minus HF, I believe, because it's falling, right? So that's a positive, that's the distance, yeah? Times what? What's the magnitude of the force of friction? Times the force of friction, right, FF, which would be mu m1g. So there you go, that's the energy at a later time, when it has final velocity vf I mean, you can tell exactly how much energy it is in terms of how far M2 has fallen, right? The further it falls, the more energy it loses. Yeah? So. All right, well, I hope this example is helpful to you guys. Let's do a rather different example here. If I can find my thing. Oh, man. Oh, there it is. Let's calculate the... What'd I do? What have I done? Oh, man. It's cold. Did I say something? I mean, okay. It's probably like a job interview or something important. That's the only reason you'd miss my class. What's more important than physics? Oh, that's easy.
Sleep?
Sleep. Just sleep, Jesus. I'm sorry, I was looking for math.
Oh.
But, just kidding.
What is that?
I'm just kidding. Physics. These are not clearly distinguishable items anyway. The line between physics and math is very blurry. If there is one at all. Okay, so, I mean there is, but. All right, so suppose let's see here. We have example 3. Let's see if I can get this one right. Suppose you have like a coffee can, all right? And, oh, I'm sorry, I'm not ready for this example. Bad things will happen if I try to do this. I need to think about this one before I do it. I was going to show you we can actually like calculate the, if we put like a coffee can full of cheese or something, and then put like a little mass on it, and then like give it a little shove, it'll wobble back and forth, and we can calculate the period of the wobbling, sort of by analogy to the simple pendulum, and the mathematics there. Did we ever do the mathematics for the simple pendulum in here, though? I feel like no. See, so this is why we should put this to another day when I'm ready. So the example I wanted to do for you guys was, let us suppose that we have a force which is equal to 3 newtons minus 2 newtons and 10 newtons. All right, and you're applying this force at radius r equal to, oh, I don't know, 10 meters minus 4 meters and 7 meters, all right? Find the torque produced by this force. All right, so here's a picture, very schematic, very sketchy picture. Here's my R. I'm applying the force here like this. My question is, what's the torque produced? How do we calculate that? All right, I'm going to give you guys about 3 minutes to work this out. When I come back, I will have other things. Do not leave. All right? No leaving. You should calculate the cross product part of it. I'm looking for you.
Oh, not, wait, wasn't that the equation you said was wrong? I found it is 4 steps. Oh, it was correct. I don't know if it's right. Yes, yes, I know it is 4 steps radius. Yes. That's why I was asking, because I remember. Yeah, but I didn't know, I just, that goes to the same.
I feel like I'm doing the cross product wrong. It's all design.
Because the order is important, I know that. I'm pretty sure.
Yes, it is. It's right there. No.
No, I did that wrong. Yeah, I did that wrong. Cross product. Yeah, there's something here. It's gonna be 3, 2, 4, 7,
Yeah, the new 26, positive 79, positive 8.
I think my values are way off.
You're making class.
Something else.
You got food? I'm a little hungry.
All right. So sorry for the delay. So we calculate the torque from the cross product. So we take R cross F, which is going to be 10 minus 4, 7, crossed with 3, minus 2, 10. I'll pull out the Newton meters out here. All right. And so that is minus 4 times 10 minus 7 times minus 2, comma 7 times 3 minus 10 times 10, I think. And then 10 times minus 2 minus 4 times 3, which, cleaning it up a bit, is minus 40 plus 14 minus 26 minus 79 and minus 8, of course, Newton meters. Is this what you guys got? All right, we can check ourselves. If this is right, the dot product of this vector and the radial and the force, those dot products should be equal to 0. They're not that easy to check here, of course, but 3 times minus 26 plus 2 times 79 minus 80 is equal to 0, and this gives me, minus 260 plus 4 times 79 minus 56, which apparently is also 0, because either I got the same wrong answer as the people up here, or I'm right. So I'm going to trust them to not really check my answer, if you guys don't mind. Question: what's the angular velocity? The angular momentum here? Let me ask a different question. What's the momentum here? Can you guys tell me that? The answer to both of these questions is who knows? I haven't given you enough information. I just told you the position and the force applied. I didn't even tell you that that was the net force, right? So it could be that there's other forces. This is just the torque due to that particular force. So anyway, this is all we can really answer with the information that's given. But anyway, it makes a nice test question, if nothing else. Anyway, I think that's all I got for today. It's just purely coincidental that we're, approaching the time of course evaluations, kind of, sort of. It's not like I just bring home-baked cookies to try to influence you or something. But I do happen to have some cookies that my wife made up here, as well as milk and cups. If I don't have enough, I have more in my office, I'll go get them. To be clear, we are celebrating the shutting down of the Department of Education. So, I really should be wearing the MAGA hat to properly incense people, but oh well. It can't be perfect. Thanks, guys.
Ian, when did they vote on it? Ian, when did they vote on it?